I just ran chaos experiments in my API running in our EKS cluster under load, and one of them really wrecked it. In this video, we'll replay compute, memory, and network failures using AWS Fault Injection Simulator. And I'll show you the exact experiment that had the worst impact on our cluster. Hi everyone, my name's Rob from RobOps, and today we're going to be testing out AWS Fault Injection Simulator as part of our EKS Experiment series. AWS Fault Injection Simulator is a managed chaos engineering service that allows you to run controlled failure experiments in your AWS environment. In this video, we'll be running 4 unique experiments that represent real-world examples of potential outage situations. Each experiment will be done on our Go API running in our EKS cluster. The endpoints will be loaded using K6 and supporting approximately 20 requests per second for each experiment. At the end of each experiment, we'll show the K6 results and how our API performed. If you're interested in the cluster setup or how I built the API, I have videos linked in the description where I do a deep dive on each. In addition, all experiment templates will be available on my GitHub page in their own repository. Leave a comment Terraform if you're interested in having these templates converted into Terraform for your own reuse. And with all that said, let's jump into our first experiment. Our first experiment is going to be a CPU stress test. This is going to target pods in our API namespace and apply CPU pressure to them while our cluster is loaded. Our cluster has a horizontal pod autoscaler enabled. We expect that as the CPU pressure is applied, our horizontal pod autoscaler will trigger and it will scale our pods horizontally to support the new load. Each experiment will be executed from the AWS Fault Injection Simulator console and run for 5 minutes. Once kicked off, we'll monitor the experiment using kubectl and Grafana. In our experiment view, we'll have a terminal watching our API namespace, a terminal running our load tests via K6, and 2 browsers monitoring our endpoint utilization and our pod utilization across CPU, memory, and network. All right, and that wraps up experiment 1. As we can see, the cluster performed actually quite well. We had a 100% success rate with a P95 latency of 1.59 seconds. As you can see in the K6 results below, we had about 17.5 requests per second and 100% of the checks succeeded. This means our cluster performed pretty well. We do have a horizontal pod autoscaler that will scale out to a maximum of 10 pods to support the CPU pressure. And so as we can see, the cluster performed as expected and we supported 100% of the load. Transitioning into experiment 2, we're going to apply memory stress. And so each pod has an allocated memory that it can support. And if we start to exceed that, we should see the pod scale out to support the additional memory pressure. And so it may not necessarily trigger our horizontal pod autoscaler, but as the pods start to slow down, we should expect some scale out. Let's see what the experiment says. And so coming to the results, we see that our cluster did not perform well at all. We ended up dropping about 20% of our requests, and we can see through the experiment that our pods really did struggle. We had a max P95 latency of about 5.5 seconds, meaning that the user would have been hanging for a significant period of time before they got results back from our API. This memory stress really shows how our cluster was impacted. And as we saw through the experiment, our pods actually didn't scale out as we would expect. And so we can easily fix this by adjusting our horizontal pod autoscaler settings to scale on memory usage as well as CPU. Next up is network latency. In this experiment, we're going to apply latency throughout our cluster and see how our pods and subsequent requests react. In this test, we would expect some requests to take a much longer period of time due to the injected latency, and in some cases, some of these endpoints might actually fail. We also, again, wouldn't expect our cluster to fail because this is just representing a slow network. So let's jump into the test and see what the results are. Similar to our memory, our cluster did not perform very well. We ended up dropping 17.5% of the requests, with a majority of them across all of our endpoints, including our compute and user endpoints for both GET and POST requests. As expected, the P95 latency was actually much more significant at 8.62 seconds, meaning that a lot of these requests ended up hanging and not actually getting back to the user. Unfortunately, things like network latency are not easy to build against. Really, what we would need to do is build this into our application code and make these requests more resilient to bad network calls. This means that when a request doesn't get a response back as expected, we would just forward it along a secondary response or a fallback. And with that, let's jump into our last experiment. All right, in this last experiment, it's a bit different from the last three in that we are just going to ask Fault Injection Simulator to randomly delete a pod in our API namespace. In our case, during the experiment, we'll have 2 replicas running, and so it would be supporting 50% of the load on each. When we delete a pod, I would expect that the pod would come down and the subsequent load would be transferred to the existing single pod while Kubernetes brings up a secondary pod. I would expect very little interruption as part of this test, but let's see what happens. And here are the results. As expected, our cluster did perform quite well. We did drop a very small percentage of requests, and these would likely be the requests that were in flight at the time that the pod was being deleted. However, I would largely say that this was a successful test, as we only dropped 3% of the requests and our latency, even at the P95 level, stayed within the range of reasonable for our users. In summary, our cluster performed pretty well in the CPU stress and the pod delete scenarios. This is because this is kind of Kubernetes native behavior. Kubernetes will always try to keep loads running on healthy pods, which is why our pod delete use case worked out well. Our CPU stress use case worked out well because we had a horizontal pod autoscaler in effect that scales on CPU stress to prevent degradations like this. Unfortunately, we don't have that same control in place for memory, and if we were to add this, I would expect the performance of our memory stress test to improve. On the front of network latency, this is something that would not improve with tweaks to our horizontal pod autoscaler. We would have to make tweaks on the application code side to allow our requests to respond gracefully in the case of long-running requests caused by latency. Anyways, I hope you enjoyed this video. If you want the templates, the experiment templates, they are linked in a repository. And like I mentioned at the beginning of the video, if you do want these put in Terraform, please comment below and I will work to update the repo with the Terraform so you can just apply the Terraform to have your own set of experiments very similar to this one, ready to go out of the box. And with that said, that's going to wrap up today's video. I hope you enjoyed it. If you did find it interesting, please like and subscribe. It really helps me out. And if you're interested in specific content, please comment below. That being said, my name's RobOps, and I hope you have a great week. Bye.